In this section, we will be looking at redox titrations. Redox involves the process of oxidation and reduction. This equation shows a general equation for a redox reaction. An oxidizing agent would react with a certain number of electrons to form a reducing agent. So we see that the oxidizing agent pulls electrons from another substance, and the reducing agent will force another substance to accept the electrons. Together, the oxidizing agent and the reducing agent are known as a redox pair. Redox pairs in redox reactions are kind of similar to how we have acid-base conjugate pairs in acid-base reactions. Here are some redox half equations. Can you identify which are the oxidizing agents in each of the reaction, as well as which are the reducing agents in the reactions? Press pause to attempt the question yourself, then press play when you are ready to see the answers. Okay, so these are the answers. The oxidizing agents are highlighted in red and the reducing agents are highlighted in green. In this example, it is very obvious because the electrons are written in the equation. So the side that accepts electrons is obviously the oxidizing agent, and the other side would be the reducing agent. What if the half reaction was not written out? You can take a look at the oxidation numbers to determine which is the oxidizing and reducing agent. The one with the higher oxidation number is the oxidizing agent, while the one with a lower oxidation number would be the reducing agent. In redox reactions, every half reaction has a standard reduction potential. A reduction potential is a measure of how favorable it is for the compound to gain electrons or to be reduced. So if the reduction potential has a high positive value, it means the compound is very easily reduced and it will be a strong oxidizing agent. On the other hand, if reduction potential is low or it has a negative value, that means the compound is a strong reducing agent. What is the purpose of looking at standard reduction potentials? We can use it to choose reducing agents and oxidizing agents for a redox reaction. A compound with a higher reduction potential will oxidize the compound with a lower reduction potential. So if we were given a set of half reactions with the standard reduction potential values, how would we know which is a strong reducing agent or which is a strong oxidizing agent? Remember that the higher the reduction potential value, the more likely it is for reduction to take place. And the lower the reduction potential, the more likely that oxidation would take place instead. So for Ce4+, since reduction is very likely to happen, Ce4+ is a very strong oxidizing agent. Similarly, since the reduction potential of MnO4- is high, MnO4- is likely to be reduced and therefore it is a strong oxidizing agent. As we move down the list, the oxidizing agents will become less and less strong. Now, how about the reducing agent? At the bottom of the list, oxidation is more likely to happen, which means that iron is more likely to undergo oxidation to become iron 2+. Therefore, iron would be a strong reducing agent. As we move from the bottom to the top of the list, the reducing agents would get less and less strong. Let's take a look at reducing agents and oxidizing agents. Reducing agents, especially the strong reducing agents, are not stable in air because they are easily oxidized. Reducing agents are often used to determine the concentration of moderately strong oxidizing agents. Two common reducing agents which are used in titrations are shown here. Ferrous ammonium sulfate is a fairly weak reducing agent and it's commonly used in the back titration of dichromate. Sodium thiosulfate is a moderately strong reducing agent, and it's commonly used in the back titration of iodine. Oxidizing agents are used as titrants when the analyte is a reducing agent. A common oxidizing agent is potassium permanganate, which is a strong oxidizing agent, and it has been used for a very long time. It is useful for titrating against weak and strong reducing agents. Cerate sulfate is another strong oxidizing agent, and it's just about as strong as permanganate. Potassium dichromate is a moderately strong oxidizing agent, and just like permanganate, it has been used for a very long time. Iodine is also commonly used in redox titrations. Take a look at the redox half equation. Iodine is an oxidizing agent, while iodide is a reducing agent. There are two main classes of titrations involving iodine. When the analyte is a reducing agent, a direct titration can be carried out between the analyte and iodine. But if the analyte is an oxidizing agent, then it can first be reacted with excess iodide to produce iodine. The amount of iodine is then determined through titration with sodium thiosulfate. So the first chemical equation here shows the reaction between the analyte and iodide to form iodine. And the second chemical equation shows the reaction between thiosulfate and iodine. Let's take a look at some examples of redox titration. Direct titration with iodine is used in pharmacopoeia assays of ascorbic acid, which is vitamin C, dimercaprol injection, and acetazole. Let's take a look at the assay of ascorbic acid injection. To the sample containing ascorbic acid, sulfuric acid is added to provide an acidic medium. It is then titrated with iodine using starch as an indicator. Starch is colorless, but in the presence of iodine, it will turn blue-black. This helps us to detect the endpoint for the titration. Now let's take a look at an example of an indirect redox titration. For this, let's look at the assay of phenol. In the first step, to 25 ml of phenol solution, add 50 ml of bromine and 5 ml of HCl, allow to stand. Then in the second step, 5 ml of potassium iodide is added, shaken, and thirdly, the solution is titrated with 0.1 molar sodium thiosulfate using starch as an indicator. So what happens at each step? In step 1, bromine reacts with phenol, and you can take a look at the chemical equation. So 1 phenol reacts with 3 bromine molecules. In step 1, bromine is intentionally added in excess. So now there would be some excess unreacted bromine. So in step 2, the excess bromine is reacted with iodide to release iodine. Here, iodine is also intentionally added in excess. And in step 3, the excess iodine that did not react with bromine is determined through titration with sodium thiosulfate. Through calculations, we can find out the amount of excess bromine and therefore the amount of phenol in the sample. Let's take a look at one more example of an iodometric reaction, which is in the assay of penicillin degradation products. So let's look at the structure of penicillins, which is on the top right. Penicillins have a beta-lactam ring, which is highlighted here. And penicillins require this beta-lactam ring to be active against the bacteria. However, the beta-lactam ring is unstable and can undergo hydrolysis. Hydrolysis of the beta-lactam ring causes it to break at this point, and the ring will open, which inactivates the penicillin. The open lactam ring can react with iodine, and 1 mole of ring-open penicillin will react with 8 moles of iodine. So in order to determine the amount of ring-open penicillin in a sample, excess iodine is added to the sample, and unconsumed iodine is determined through titration with sodium thiosulfate. The pharmacopoeia specification is that the amount of hydrolyzed penicillin should not be more than 5% of that obtained when all penicillin in the same amount of sample is completely hydrolyzed and then reacted with iodine. In other words, the amount of hydrolyzed penicillin should not be more than 5% out of the total penicillin in the sample. The endpoint in redox titrations can be determined by potentiometric detection. Many redox titrants are also colored, for example, permanganate or iodine, and therefore the endpoint can also be detected visually. Besides visual detection, a photometric detection can also be used to follow the course of the titration, and this will allow for automatic titrations. For titrations involving iodine, then starch can be used as a chemical indicator to provide that visual color change. Redox titrations are used in a number of pharmacopoeia assays for ferrous salt, hydrogen peroxide, benzoyl peroxide, dimercaprol injection, and ascorbic acid.